Okay, you're on the air, and we are talking today about significant digits once again, and we're in particular we're going to talk about doing calculations with significant digits. This is very similar to what you would call the propagation of error in more kind of exact terms. We don't get into, we talked about using plus or minus notation. And if you get into more sophisticated levels, like, for example, if you took analytical chemistry in college, that's what you would start using. You would start using plus or minus notation and confidence intervals and stuff like that, rather than just relying on significant digits to keep track of your uncertainty. But in this class, we're going to use significant digits. We are not going to use the plus or minus notation, at least not on a routine basis. So Sig Figs is what you need to know how to use. Something's bogging this thing down today. And the basic, there's really only two rules when you're doing calculations with significant figures. Does anybody know what they are? One is for when you're multiplying or dividing. One is for when you are adding or subtracting. You want to help us out? Jojo. So, okay, count sig figs. So you have to know the number of sig figs, and then you said you're going to use that. Okay. So we're going to call this calcs with sig figs. In fact, the only reason you would ever really want to count sig figs, which is what we were doing yesterday, is so that you could have the correct number of sig figs in your answer when you're doing a calculation. So when you're multiplying or dividing, let's just do a very simple problem. Let's say I'm going to do 2.0, and I'm going to multiply that by, let's say, 4.00. My answer, of course, is 8. But what happens is I'm going to be limited to the smallest number of significant digits. So the number of significant digits in your answer it's limited by the data point with the fewest significant digits. And you might find it weird that we don't go by decimal places, and that's an important point. We do not, when we're multiplying and dividing, we do not go by the number of decimal places in the data points. We go by the number of significant digits. And the reason is when you're multiplying or dividing, what happens is the result is dominated by the percent error. So let me give you an example. Let's say we are measuring something, and we're going to measure the area of this thing. And let's say that I say that it is roughly 1 meter long, and I'm only using one significant digit, right? So, but then when I measure the length, I use a stick that's 1 meter long, and maybe it doesn't have any divisions like for centimeters on it or millimeters. So I just say, oh, it's roughly 1 meter long. So that would be 1 sig fig. That means that that's uncertain. So we're uncertain at the 1 meter level. And then let's say I use a different thing like a ruler, a 30 centimeter ruler to measure the width. and I say that this is 10.0 centimeters, which has 3 sig figs. All right. Now, in this case, and first thing I'm going to do is I'm going to say that my width, let's express this in terms of meters. It's 1/10 of a meter. That's my width. And then the length is 1 meter. It's got 3 sig figs, and 1 sig fig. Well, what does this really mean? So if we kind of think about what we were talking about yesterday with the plus or minus, as I said at the beginning of the sig figs section, significant digits is really just a kind of a rough and dirty way of dealing with uncertainty. It doesn't give you as much information as plus or minus. What we're saying here is that this thing is uncertain, that's 0. So that means that this number could actually range from 0. Well, let's see. What would round to? The question is, what would round to this number point? It would be 0.1. Something like the high would be this, right? If the number were that high, it would round to 0.100, and it could be as low as right? Now, in this case here, this one would be as high as 1.4, right? Or as low as 0.5. You follow me? And actually, wait, this underestimates the error. I can go up as far as... No, that was right. What was this one? This one I had going up to this, right? And this was... No. 0.95, right. Does that look better? It can, but this is like the minimum that it would be. Yeah, I should work this out before. Anyway, what's going to happen here is because this error is so much larger, it's going to dominate the answer. So how would we get... Go ahead, Raja. Right. Yeah. Yeah, the idea of rounding, and the purpose is, so as an aside here, the only thing, a lot of people get confused about this odd even rule with rounding. It's only applicable in very specific cases. So like in this case right here, if all you have to base your whether you're going to round, if all you have is that 5 on the end, so in other words, there's nothing after this to tell me that it's definitely over the halfway point, greater than half, then you use a rule that is, if this number is odd, then you round up. If it's even, then you round down, right? So what you're saying is that it's weird that this would round to 0. Is that your point? Yeah, the main idea here is that if you always round up when you have a 5, when the number ends in a 5, then you're going to bias your data. You're going to skew your data upwards. This might not be noticeable with only a small number of data points, but if you had a large data set and you were doing this routinely, you would actually end up skewing your data slightly and noticeably upwards. So in cases like, well, let's look at a few examples, I guess, before we move on here. In cases like, say you have a number like this and it says round to 2 decimal places. This is where you have to use the rule, because you might have been taught in the past that whenever it's a 5, just kick it up. So I would write 0.11. But with the rule, if we consider 0 an even number, then we're going to say 0.10. However, if I had this, then I would round this to 0.12. See how that works? Now the important thing to remember is that the only reason we are, well, there's a couple things to remember here. This rule, the odd-even rule for rounding, it applies when you are rounding the next to the last, you're rounding to the next to the last place or digit. That's the only time it's going to apply. It's a very specific situation. I'm trying to round to this place, and I only have one more digit after that. Because if I had another digit, then it would be easily decided, right? Anything else on this side would push it up. Follow me? Yes. However, there are cases where that's not exactly true. If these are all zeros, then I still have to use the odd-even rule. But if there's any non-zero digit to the right of that extra digit, then I don't have a problem. I know that I'm going to round up, because it's going to throw it over the halfway point. Yes, Cassidy. Yeah, sure. Okay, so just to wrap this up here, what I'm going to do is just calculate two areas, the highest possible area and the lowest possible area for this rectangle. So the highest possible area would be the high end of both of these multiplied together, right? So I would have the area and then the lowest possible area would be the two lowest values multiplied by each other. Whoops. And let's see. The average of these is 0.18806. What would be my plus or minus value on these? I've got, I could subtract either of these, so let's just take 0.14056. It's plus or minus 0.05. So I would write 0.19 plus or minus 0.05. Now, what is this in terms of percentage? This is 0.05 divided by 0.19, 26%. So I've got a 26% error. This thing right here, though, what was the error on this? It was only, let's see, 0.1234. This was a 0.4% error. But how about this one? The error on this one is 0.4 over 1. This is 40% error. So, and actually, this is not working out quite right here. So, what happened?
Why would you add the two areas together?
Where? Which one? Oh, this is messed up, isn't it? Yeah, what's up with that? Okay, sorry. Thanks. I didn't divide by 2. Yeah. Okay, so 0.9403, and then we have 0.14056 minus 0.09403, and it's still 0.05, but now it's 0.09. Okay, this makes more sense, because this error should come out roughly equivalent to the largest one down here. So we're going to say 0.05 over 0.09. There we go. It's actually more like the sum of these two errors, you add the errors as a percentage. And so my point here is that you might as well have just used your rough meter stick to measure the width because you wasted your time here. You destroyed your data by using this sloppy point right here. This is critical when we're doing labs. I'll give you the best example. We have actually the lab we do next week. It uses some very precise instruments. It uses something called a pycnometer to measure the density. It's a very precise volumetric flask. It'll give you like 4 decimal places. It could, potentially. The balance we're going to use will give you 4 decimal places. However, we have to use the density of water at one point in the calculation, which we could get to a lot of decimal places if we wanted. There's calculators on the internet that'll give you that. Unfortunately, our thermometers will give us 2 or 3 sig figs. So what happens is when you take that into account, that means your density of water is only going to be estimated to 2 or 3 sig figs. And that is going to carry through to our final answer, which means our density won't be any more than 2 or 3 sig figs. So even though we have all this fancy equipment, because our temperature measurement, we don't have similar equipment to measure that, we basically might as well not use all the fancy equipment for everything else. Although there is an accumulative effect. You want to be a little careful with that. But if you're in an extreme situation like that, then that could actually be true. So it's always, and I think it's something that you need to, in fact, probably the most important thing that happens in these labs, when I took chemistry as an undergraduate, I got a C both semesters. When I took 127, 128. It didn't have anything to do with the fact that I was in the back of the room writing letters to my fiance during class. What it had to do with was that when I was in this was before email. When I was in, there was a time before email. It was not that long ago. When I was in the lab, I was like, I don't know, I was so uptight. I felt like I had to do everything like exactly as they said, or disaster would happen and my data would just be horrible. And that's a very inefficient way to operate. So that's the main point of that, is to read your labs beforehand and make sure you understand it so that you know at which points in the lab do I have to be very careful and patient and exact, and at which points do I not have to worry about it. See what I'm saying? If you're filling a beaker that's only going to be a hot water bath, so you're just going to heat it up and put something in it to heat up, then it doesn't matter at all how much water is in the beaker. So if it says put 300 milliliters of water in a beaker and heat it up as a hot water bath, it doesn't mean 300.0000. See what I'm saying? So this kind of thing, thinking about uncertainty and what uncertainty is important, what is not important, is really critical. Think about what calculations you're going to be doing. Is this measurement that I'm making going to be part of my final calculation? If it is, then it probably does need to be as precise as you can make it. So always think about these things. Measurement is a key part of science. All right? Yes? Right, one uncertain digit. So yeah, let's just clarify that a minute, because I don't think I did anything like this last time. Let's say I've got graduations on, say, a ruler. So let's say this is a ruler. And if this is 0 and this is 1, so this is 0.5. If I had some object that measured to right here, then what I would do is I know for sure that it's greater than 0.5. I know for sure that it's greater than 0.6. I know for sure that it's less than 0.7. I'm allowed to make one estimated digit in between there, so I'm going to say 0.64. Now you might dispute the 4 on me, with me, and that's fine. You might say 3, you might say 5. And that's where the uncertainty comes in. So this is my one uncertain digit. So what some of you were doing with the cylinder was to kind of add a bunch of digits here. So it doesn't make any sense. And even, you know where it's tempting, where it's really tempting to do that, is if you think it's about a quarter of the way, then you'll be tempted to write this. Don't do it. Because you just put 2 uncertain digits on there. If you thought it was a third of the way, you might be tempted to write this. Don't do it. All right. If you thought it was an eighth of a way, you might be wanting to put, like, what is it, 1625 or whatever. No, don't do that kind of stuff. Okay? All right, so what was this? This was just this part right here. I was just trying to kind of explain the theory behind this, why we go to the smallest number of sig figs. It's because that least precise number, the error in that number dominates the error in our answer. It's like the weakest link. One sloppy data point and everything's gone. That's how it works. Now, by the way, a lot of people ask things like, what about if we're doing a calculation where we've got something raised to an exponent, right? Well, if you're raising something to a power, it's basically a multiplication operation. So still do the same thing. Go with the number of sig figs. If you're doing a logarithm, same deal. Yes. Yep, so if I had 2.0 divided by 4.00, I'm going to get 0.50. Right, places don't matter. Remember, we could express these in scientific notation and make as many decimal places as we wanted on either number. Right? If I put these in scientific notation, I could express them both as powers of 10 to the 27th, you know, or times 10 to the 27th, and I'd have huge numbers of decimal places. So decimal places don't matter when we're multiplying and dividing. When we are adding or subtracting, different story. So adding or subtracting. Here we go by decimal places. Not sig figs. So let's do an example here. We've got 2.0 plus 4. Well, this is going to come out the same. Let me pick something different here. There we go. That'll do it. All right, we have to make a little discrepancy here. So if I were to add this together, here's what I'd do. I would first, I'd go ahead and carry these down. Now the reason I would do that is there's some difference of opinion on this, but I think the majority of statisticians and people would say you keep all your digits until the final answer and then round to the correct number of decimal places or sig figs. So in a multi-step calculation, keep all your digits, or at least keep an excess of digits. Keep a couple extra. So if you think you're going to have 2 decimal places in the end, keep an extra couple. That helps to eliminate rounding error. Yes. Same thing at each step. So here's a convenient way to do that is I'm going to use these 2 numbers. I'm going to write these 2 numbers down. I'm going to put a line under them, which reminds me they're not significant. They're not significant. They're like virtual numbers. And then down here I've got 1 and 2, and then 6 and 1. So what I'm going to do, this is going to end up looking the same as it would if we went by the number of decimal places. My final answer is going to have 2 decimal places. Let me see, I got to get a better example. We're limited by that. Let's do... Well, if we do it, let's do a subtraction here. 12 minus 4.2157. If I got 12 minus 4.2157, I get 7.7843. Those are not significant, but I'm going to write them down when I first do this, because just in case I needed to use this number again in another calculation, I would want to use those digits. But if I'm expressing this as a final answer, then I'm going to write 7.78. Now this illustrates the key difference when you are adding or subtracting. My final answer only has 3 sig figs. Yet this one had 4, this one had 5. So I actually lost significant digits. Because when you're adding and subtracting, you don't go by sig figs, you go by the number of decimal places. Yeah.
The first one, the addition one, when you got rid of the non-sig figs.
Oh, you have to round. Yes, good point. I should have rounded this to 2. Is that what you're going to say? I cut you off.
Yeah, I was gonna say.
Yeah. Is that what you were going to say, Roger? Thanks. So, yes, round it at the end as well. But you see what happened here? I actually lost sig figs, and that confuses some people. You can also gain them when you're adding. If you go into the next place, so if, let's say I was adding 2 numbers that were both in the tens place and it went over 100, I would gain sig figs. When we're adding or subtracting, we're not counting sig figs anyway. We're going by decimal places. Okay? Questions about those rules? How about mixed operations? So if I've got multiple steps, how does it work? Well, let's see if I got a good example here so I don't have to make one up. Yeah, make one up. A good example of this would be density. Because typically you might do 2 steps, like you might have one step where you use a graduated cylinder to measure the volume by difference, and then you weigh it on a balance. So I have a graduated cylinder, and then I'm gonna measure the volume. So let's say that my initial volume in the cylinder is 50.1 milliliters, and then I drop some object in there, and the volume goes up. So the final volume is maybe 60.1 milliliters. Let's make it 61. So the volume of my object then is going to be 61.1 minus 50.1. That didn't work out like I wanted. Alright, sorry. Scratch that. Scratch it all. 59. There we go. Trying to make this work out right. So I'm going to subtract these 2 to get the volume, and I'm going to get 9.0. So applying the first rule, you can already see we're down to 2 sig figs, right? Because we're doing a subtraction. Now let's say the mass. I weigh this thing, and the mass is 28.01 grams. So then the density is going to be equal to 28.01 grams over 9.0 milliliters. And the answer is 3 point, repeating, and that is grams per milliliter, which is the same as grams per cubic centimeter. But I only have 2 sig figs here, so I have to change this. Yes?
Had the subtraction problem been different, and you were given, you ended up doing subtractions so that you would have to get rid of some things, but it was something that you would normally keep till the end. Would you divide the mass by the rounded answer, or by...
Yes. No, not the round answer. So let's do this. So I'm going to throw on a couple digits here. So then what I do when I do the subtraction, I keep those. I just put a line under them to remind me that they're out of here later on. So then I have them down here too. And I do the calculation with that. So let's see what happens, if it makes a difference. It's going to depend on how large those numbers are. So I still end up getting the same final answer. But it might not. It depends the size, relative size of those. It could change your final answer. So make sure you keep those. The problem is if you've got a lot of steps, and sometimes you'll have a bunch of steps in your calculation, every time you round, you could be generating a significant amount of error when you round. And that'll be accumulating. And so if you don't do that, just round at the end, then it's going to make it a lot better. It also makes us much more consistent with other people. All right. Any questions on those rules? All right. Why don't we try some practice? So let me